Today we're going to take a look at section 10.4. We're going to talk about Pascal's Triangle, and the very first part of it's going to feel a little bit like a deviation from what we've been doing, but there is a definite connection that we'll get to shortly. Okay? So to start with, let's just talk a little bit about what Pascal's Triangle is, where it came from. This is an unending triangular array of numbers. It is written about and credited to Pascal in 1653. But as with many other mathematical sort of discoveries, it was actually created far earlier, and there's evidence that it was studied in China and India as early as 1100 or earlier. So this is a very, very old mathematical object. He's not a plagiarist. There's another one that's very familiar to you that you give credit to that actually doesn't deserve credit either. You guys know Pythagorean theorem, right? Yeah. He didn't develop that. In fact, Pythagorean theorem, which is a little more interesting, was actually something that Pythagoras knew, and it was like a hush-hush secret, don't tell anybody, because it kind of warped their worldview at the time because it created things called irrational numbers. And Pascal wanted all numbers to be rational. Rational means something you can measure. And Pythagorean theorem proves that there's things that you cannot measure to a precise degree of accuracy without the irrational numbers. So it happens a lot in mathematics where the credit is actually given in a place that it was not first developed. All right, so we're going to look at Pascal's triangle. And at the top of Pascal's triangle is the number 1. And I'm going to develop just a few rows of it, and then we'll talk about some of the patterns within it. The next thing is that there's ones sort of on either side, creating sort of a triangular shape of ones. We go down in ones on the sides, and then the number between them on the third level here is the number 2. We go down one more time, and we have some 3s showing up. And you might be tempted at this point to think that I'm going to put a 1 here and a 1 here and fill them all in with 4s, and I'm not quite. There's a 4 here and here, and there's a 6 in the middle, and that's where I'm going to pause for the moment. So this is the first few rows of Pascal's triangle. So some patterns to recognize. The outer edges are always 1s, okay? Always going to be a 1 on the outside edge. The second diagonal down on both directions just increases by 1 each time. 1, 2, 3, 4, 5. It's going to continue on. So if I looked at the next row, you would definitely go 1 and then 5, right? So you might ask then, well, where did the 6 come from? Well, actually the 6 comes from the place that all the other ones come from, or at least it has a pattern that all the others have. 6 is actually the 2 diagonals above it, the 3 and the 3 added together. And it's actually true for the other numbers as well. It's just that we have other patterns that are seemingly more apparent, right? So the number 4 is the 1 and the 3 that are above it. And you could even say that it's true about this 1 because there's only 2 above it, but there's only 1 thing above it, not 2 things above it. It's the number 1, so it is the summation as well. So with that in mind, let's develop the next row together. So we've got a 1. What would come next?
5.
A 5. And then what would happen?
A 10.
A 10?
A 10.
Mm-hmm.
5. 1.
Okay. That's perfect. Does everybody see where all the numbers came from? Okay. You might also notice, I didn't mention it before, but it's definitely apparent, I think, at this point, that there's some symmetry involved from the left to the right-hand side of this, right? So whatever it starts out with, you might duplicate the middle value, you might not, depends on if there's an even or an odd number on the row, and then you repeat them going down. Right? There's symmetry from the left-hand side to the right-hand side. Let's do one more row for now. We'll come back to this in a minute, but we'll do a 1. What's the next one?
6.
Mm-hmm.
15. 20. 15. 6.
And then 1 it ends up with, right? Yeah. Okay, is everybody good? Okay, I want to show you a few other things that are going to be helpful for us as we connect some pieces to what we've been doing recently. I'm going to label this over here on the side as to which row we're on. And I know it's going to feel a little bit awkward to call the top row row 0, but I really need it to be row 0 for Y connections later. So we're going to start with row 0 as the top row. So in order to try to keep these sort of in line, I'm going to put a highlighted yellow piece along the way since I don't have like lined paper, but it will be okay. So that's row 0, row 1 would be the next one. We're just increasing as we go. This is row 2. The reason I kind of want, at least one of the reasons I want my rows to be labeled like this is because on row 2 I want it to have the number 2. Does that make sense? So on row 3, it actually contains the number 3. Oops. Is everybody good with that? So let's label all of our rows going down. So we had row 3. I'm not lining these up very well. Okay, we have row 4, row 5, and row 6 are the ones we've done so far. Is that good? Okay. I'm going to look at one other pattern that shows up from Pascal's Triangle. It's a very interesting one. We're going to just write it over here on the right-hand side. And I'm going to try to stay in the dark piece right here. And it's the sum. So what I'm going to do is I'm just going to add everything up along that row. So along row 0, the sum is 1. Along row 1, my sum is what? 2. How about row 2?
4.
Row 3?
8.
Row 4?
16.
Okay, we're just adding values up. If you're seeing what we're doing, we're just adding them together. Any idea what row 5 might be?
32.
I don't think you're adding anymore, though. What's your next one? Do you know it? So now we are adding. It is 64. Okay, so maybe we're adding. You're just adding fast. Okay, so this is the summation. What I'd like for you to do, though, is to look at these values and see if you notice a pattern in the summation of the values.
Doubling every time.
They're doubling every time, right? So if I wanted to know what the summation of the next row is, I don't really need to add it up. It's going to be
64 from 64.
at plus 64 plus 64 or 128. So it's doubling, it's adding to itself, or it's multiplying by 2 every time. There's another way that you can think about the connection. So I'm going to actually draw that one in here. These are multiplying by 2 every time. Okay, so that is one way of thinking about it. The other way of thinking about it is that they are actually powers of 2. So I'll start with this one right here because it's easiest to see. This is 2 to the power 1. 4 is actually 2 to the power 2. 8 is 2 to the power 3. 16 is 2 to the power 4. 32 is 2 to the 5th, and 64 is 2 to the 6th. And while I didn't write it in, it's actually the top. This is 2 to the power 0. 2 to the 0th power is 1. The reason that this might be, depending on what you're looking at, a beneficial perspective, instead of noticing what we did over here where it's the multiplying by 2 every time, is because this right here shows us that we can actually choose any row we want. So we can say, hey, what about row 10? Okay, well, it's 2 to the power 10, right? I don't need to know all the pieces in between. Whereas if I'm thinking about it as a multiplying by 2 every time, I'd have to actually find all the in-between pieces to get to it. If it's 2 to the 10, it wouldn't take me very long, but if it was 2 to something much larger, it might, right? The difference between what we're doing is types of formulas. So when you need the numbers in between, like when you're multiplying it every time by 2, that's called a recursive formula. It means I need to know the step before to get to the next, and I need to know the rule or the pattern to get to the next step. But when I'm actually using it like this is a general pattern, or a general or an nth term is how they're defined. So they're just a different way of thinking about them. There's not really a way that's always better than another, but they're beneficial in different ways. All right, so we need to make a connection. Obviously, what in the world does that have to do with what we've been doing? Because it doesn't look like there's one. And it's actually a very interesting connection. So I'm going to switch my screen, and I'm going to draw Pascal's triangle again, at least a few rows of it. But I'm going to write into that what the connection is. So there are combination values inside of Pascal's triangle. The top of Pascal's triangle is 0C0. If I move down from there, I have 1C0 and 1C1. And then I have 2C0, 2C1, and 2C2. I have 3C0, 3C1, 3C2, and 3C3. I'm going to go a couple more deep and then we'll stop. 4C0, 4C1, 4C2, 4C3, 4C4. We'll do 5C0, 5C1, 5C2, 5C3, 5C4, and 5C5. I can continue this, indefinitely as well. So what is this telling us? Well, there's a very interesting connection between the structure of the triangle before and its values and combinations. For example, we're going to choose one randomly. I'll do this one, 5C2. I'm just going to calculate with you 5C2. We know how to do that because we did a whole section of combinations and permutations. 5C2 says I have 5 factorial on top. I have 5 minus 2, which is 3 factorial, and 2 factorial on bottom. So I'm going to write my 5 out. 5 times 4 times 3 factorial. And there's that 3 factorial. And then 2 times 1. 3 factorials cancel. The 2 reduces with the 4. And then I have 5 times 2 is 10. Okay, is that good? You'll know how to do that. We've done that already. This is 5C2. But take a look. These are all labeled by the row they're on. So this is the 5th row, and it is the second entry after the number 1. So over here, the 5th row, and the second entry after the number 1 would be this location. And what number is there?
10.
It's a 10. That's good news. Because what that means is that at least for as many rows of the triangle as that I have, I don't have to actually calculate 5C2. I can just find its location in the triangle.
That's fun.
And it works for all of them. It's very clever. So we're going to do an example of one that we've already got rows enough for, and then we're going to do another one where we don't quite have enough rows. We're just going to fill in our rows to find it. So this one is going to be 6C3. So I need to be on row 6. Okay, so this tells me the row. And this number tells me the entry, how about we say value? The value, I don't want that word either. How about location? That's a good one. Location. The location after 1. So we never count the first 1 in my number columns, okay? We got to start counting after that. So this should be row 6, and it's the third value after 1. So row 6, so I'm on my last row that's on my thing. This is the first value after 1, the second value after 1, the third value after 1. The value should be 20. So over here, this is simply 20.
We could just do the math to prove that.
You could do the math to prove that, exactly. So if you wanted to confirm it in another way. So now the cool thing is for small values, you have 2 ways of making sure that your answers match. That's actually really helpful, right? It's almost like you have a back of the book to check with, right? You've got 2 ways of doing it. They both should be the same. If they're not, there's an error in your work somewhere. Now you need to figure out which one has the error. Now the next one we're going to do here, 8C6, I don't have row 8. But we're just going to develop our triangle out a little further so that we do. Okay, so I'd like for you to work with me to find the next row. So row 7 will be next. So what will row 7 say?
1, 7, 121,
Mm-hmm.
35, 45, 21, 7,
Yep. And once you get halfway, you can just repeat the values backwards, right? And then we need row 8 for our example, so we'll go to row 8. So I'm going to have 1 and then 8, and then what?
28,
Mm-hmm.
56, and 56, 28, 24.
Well, this is 70, because this some of them double in the middle, and some of them actually just have a single value. It depends on how many. So this one has 70, but then it goes back, like you said, Bryn, to 56, 28, 8, and 1. Okay, is that all right? Okay. So this says I need to be on row 8. And it's entry 6, right? The 6th value after the number 1. So again, ignore the one diagonal part. But I'm on row 8. That's the last row. So this is 1, 2, 3, 4, 5, and 6. The answer is 28. Okay, is that good? Okay. So we can simply read the values off, but we can actually use them within a word problem as well, like we have been using back in sections 10.3. So our next example is one like that. Suppose we have a committee, and please remember that anytime you see the word committee tells you that you're working with a combination. So notice these are only for combinations. I don't have sort of an analog for permutations. There's not a triangle that has permutations in it. It's just a combinations triangle, okay? So I can't use it for everything from 10.3, just for the combinations. So I'm going to have a combination. Committees mean combinations. My committee is going to have 3 people, and they're going to be selected from among, I have 7 women, and I have 3 men. And then our committee is going to have certain structures that are given in problems 3 through 6. So problem 3 says that I want exactly 3 women. So what we have to figure out is what the combination structure is. It's a combination because it's a committee. What are the values on either side of my C for this particular problem?
7, 3.
Right, there are 7 women. My committee is supposed to have 3 people. So from among the 7 women, I select 3 of them. This is 7C3. So that part I have to do sort of on my own. But once I have the 7C3, I can come back over here. I'm on row 7. And I'm on the 3rd entry after the 1. It's 35. So 7, 21, it's 35. So 7C3 is 35. How about exactly 3 men? What would be the combination structure? 3C3. There's only 3 men to pick from. C3, I'm picking all 3 of them. So now I'm on row 3. That's row 4, I think you're looking at. Row 3. And it's the 3rd entry, 1, 2, 3, after the 1 at the beginning. So it ends up being the number 1. So you can get the number 1. It just won't be the 1 at the very beginning. Okay, it could be the 1 at the end. That's what this one was. So 3C3 is 1. And that should make sense. There's 3 men. I got to select them all. So, yeah.
We ignore the first one because the one at the end is the same.
We're ignoring the first one because that's like when I paired these up, the pairing started here with 5C0, and the 5C1 starts here.
Gotcha.
So that's why we're pairing it up and we're skipping this row, is because this is choosing 0, and we're always choosing at least 1 or more, which is the next entries in our row. Yeah. Okay, the next 2 are a little bit more involved because I have some sort of a combination of men and women. This says exactly 1 woman. So if I'm going to have exactly 1 woman, but there's 3 people on the committee, then I need 2 guys as well. So I need 1 woman. So there are how many women to pick from?
3.
7.
7.
7. And I need 1 of them. So it's 7C1. What will the piece look like for the men? 3C2. Right. 3 men, choose 2. So So I need two values out of my table, right? I need the value for 7C1, and I need a value for 3C2. So let's do 7C1 first. So what is 7C1?
7.
It's 7. It's right here. And what is 3C2?
3.
It's 3. It's this one here. So I have 7 and 3. So this is 7. This is 3, which gives me a total multiplication of 21. And the reason I'm multiplying them, by the way, is because of the fundamental principle of counting. Fundamental principle of counting says I find the number of ways one thing can happen, I multiply it by the number of ways something else can happen. 7C1 is the number of ways I can pick my woman. 3C2 is the number of ways I can pick my man. That's why they're being multiplied. Okay, last one, exactly one man. So how do I get the exactly one man part? 3C1. If I stop there, I do not have a committee of 3 people, though, right? So please be careful. Take a look. Every time we do this, we are creating the committee of 3. I selected 1. I selected 2 more. Now I have 3 people. Right now, I only have 1. So what will I also need to select?
7C2.
Yeah, 7C2. And because of the fundamental principle of counting, I'm multiplying them together. And again, I have 1 plus 2. There's my 3 committee members. Okay, so I have 3C1, I have 7C2. So 3C1 means row 3, entry 1. It's a 3, this one. And then 7C2 is 21. It's down here, second row, or second entry on that row. So this one is,
63.
yeah. So I have 3 times my 21. I have 63. And that might be a little bit not what you were thinking if you just looked at it at face value. Okay, well, I just switched the men and the women. Why did I get so many more? Well, the reason I got so many more is because I had so many more women to choose from, right? 7C2. I didn't have that many choices when I said 3C2 because there simply weren't as many men to choose from. Does that make sense? All right.